In this lesson, we're going to graph exponential growth functions. So the parent function for an exponential growth function is going to be declared as f of x equals b to the x power, where b is some base and then x is our variable. We also want to be sure that b is greater than 1. Anything greater than 1 will fall in that family of exponential growth functions. We can see that the general shape here is just kind of this curve that continuously gets steeper and steeper the further right you get with it. And no matter what your value of b is, it's always going to go through or have a y-intercept of 0, 1. And when x is 1, y is always going to be the value of b, so you'll have 1b. So if b is 2, 1, 2. If b is 5, 1, 5. And then it'll just continue to grow exponentially from there. And you can substitute in values of x and find y. Also, you want to remember that when we first talked about parent functions, this particular function had a asymptote. In this case, the asymptote runs along right here, along the x-axis. So it'll get closer and closer to the x-axis, but it'll never touch it. Okay. Also, I want to point out the transformations are h and k. This one's a little different because our h is in the exponent. Remember, we always subtract h from x wherever x might be. In this case, x is the exponent, so we subtract h from x in the exponent. H is your horizontal translation, k is your vertical. So let's graph one. I want to graph y equals 1/2 times 2x to the power of x plus 2 minus 5. And we have this 1/2, which is our a value, and that's going to be a vertical compression or vertical shrink. And so we'll want to graph that. We'll want to graph the a times b to the power of x, in this case the 1/2 times 2 to the x, and then we'll do the h. And so all of these exponential growth functions have the y-intercept of 0, 1. So we would put a point there. However, we have to multiply that by our factor of 1/2. So instead of 0, 1, it's going to be 0, 1/2. Then we'll put in the next point. Normally it would just be 1 and then b, but our b value is 2, so it would be 1, 2, but we're multiplying that by 1/2, so that's going to be 1, 1. The next value I would get would be 2 to the second power, which is 4 ordinarily. So I'd go up to 1, 2, 3, 4, but again, we got to multiply that by 1/2, so that's just going to be 2. And then 2 to the third power is 8, but again, we have to multiply that by 2, so we got to go down to 4. That would be enough points going in that direction. So I know that that's going to be having a curve going upwards like so, going through those points, and then it's going to come down, and it's not very good, but it's going to get closer to the x-axis where that asymptote lies. So given those points, 0, 1/2, 1, 1, 2, 2, and 3, 4, I can translate it 2 units to the left and 5 units down. So I'd go and take the 0 and 1/2 and go left 2, and then down a total of 5. 1, 2, 3, 4, 5. So that would put me at 4.5, or -2, -4.5. And I would do the same thing with each of the other points. So 1, 1, left 2, so subtract 2 from 1, making it -1, and then subtract 5, which would bring us down to -1, -4. Then 2, 2, subtract 2 from there, down 5, and that would put us at 3, or -3 rather. So I'd put in 0, -3 for that point. And then my last point, 3, 4, we take that left 2, so 3 minus 2, which is 1, and then 4 minus 5, which makes that -1. So that would be 1, -1. And I would connect those points like so, as best as I could. And then draw it this way, where my asymptote, now my asymptote has gone down 5 units as well. So normally it was originally at y equals 0, so now it's at y equals -5. So it's down here. And that's a really terrible, terrible depiction of it, but that's the idea. Okay, so the next topic I want to talk about briefly is compound interest. Compound interest is simply a way we can deal with money as we apply interest upon a principal. The principal is the starting amount. That's denoted by the variable P. So let's say I could deposit $1,000, and then we can put this in an account that pays interest, and that interest rate is denoted by the variable R, and this is always expressed as a decimal. So whatever that percentage is, let's say it's 10%, we'd substitute in 0.1 for R. We're going to compound that n times per year, so the number of times we're going to apply that interest, and then the T is going to be the number of years, T is time measured in years, and then the A is our final amount. So we need to be familiar with each of these variables. A, P, R, T, A, N. This is a formula that I want you to know really well and have that memorized. Okay, so in this example, let's say you deposit $5,500 in an account that pays 3.6% annual interest. Find the balance after 2 years if interest is compounded quarterly. So what we would do is we're just going to be plugging in these, or substituting these values into our variables. So the 5,500 is our principal, so that goes in the P, and the 3.6%, that's going to be going in the R, but as a decimal, so 0.036. The 2 years is going to go into T up here in the exponent, and then it's compounded quarterly, and quarterly means quantities of 4, and that actually goes in 2 places, N here and N there, and then when we work that out, that'll give us A. So let's just do that, shall we? So A is equal to 5,500, 1 plus the interest rate, which is a decimal, is 0.036 over the number of times compounded, which would be 4, and then to the power of 4 times 2. And then that's all just calculator work. and that should give you $5,908.70. So, and then you can make that a therefore statement. So therefore you would have this much money after 2 years. Anyway, that's how you graph exponential growth functions with some compound interest on the side.